Welcome. This demo presents the tool for JSON schema witness generation. Our tool is available online for you to try. JSON schema is an important formalism for declaring schema constraints on JSON documents. So here we see two JSON schema declarations. The schemas define constraints on JSON objects that have an address property. Now, how do those schemas compare? To answer this question, we need to check for JSON schema containment. Existing tools for checking JSON schema containment will tell you that the right schema is more general. It subsumes all JSON documents that are valid with regard to the left schema. However, they will not provide an explanation as to why this is the case. The tool introduced in this demo checks for JSON schema containment based on witness generation. Upon the push of a button, we can generate a witness, that is, a small JSON document that is valid with regard to the right but not the left schema. As there is no witness valid with regard to the left but the right schema is more general. Thus, witness generation provides an explanation when checking JSON schema containment. JSON schema witness generation has several practical and relevant applications. Let's discuss possible applications next. Then we have a look under the hood of our approach, which supports the negation operator as well as recursion, which is not the case in related work. We conclude with a guided tour through our tool, where we also point out the open research challenges. We believe these will be of interest both for the theoreticians and the practitioners among you.
Hi, I'm Carlo Sartiani, and I will present to you a few practical applications of witness generation for JSON schema. Witness generation can be helpful in many practical contexts, ranging from schema emptiness and satisfiability checking to schema evaluation and even schema design. And I will focus here on schema emptiness, satisfiability, and schema evaluation. Why schema satisfiability? Well, indeed, JSON schema is a very complex and powerful language. The semantics of its schema depends on a quite sophisticated interplay among multiple assertions, and some of them are imported from externally defined schemas, so you have no control on that, on those assertions. And sometimes this interplay may lead to inconsistencies or even empty schemas. This is a practical example coming from the web. In this case, we have the description of an object with two properties, options of type string and read-only of type boolean, and we have them two conflicting assertions. We require that objects have only one property through the max properties assertion, and then we are stating that both properties are mandatory in all objects. So we have a conflict, and then we have an empty schema. This is a simple example, but in complex examples where you have assertions coming from different schemas combining together, is almost impossible for a human to detect such a situation. Schema evolution, where schemas evolve over time. You are no longer in a context where schemas are fixed and do not change. So we can use witness generation for checking for schema inclusion and for schema equivalence too. Schema inclusion is quite simple. S1 is included into S2 if we cannot find a witness for S1 and not S2. Since the JSON schema has conjunction and negation, this is actually a perfectly legal schema. And so if one can find a witness for S1 and not S2, then we can find a document that satisfies S1 but not S2. And so S1 is not contained into S2. And we can exploit this for checking schema equivalence. And in this case, S1 is equivalent to S2 if we cannot find a witness for S1 and not S2, and in the same way we cannot find any witness for S2 and not S1.
Hi, I'm Giorgio Gelli, and I would like to tell you something about the internals of our algorithm. So, we start from a JSON schema, which we may describe as a system of recursive equations where each variable is bound to a complex JSON schema defined in terms of the other variables. The first step of our algorithm is to rewrite this system into a normal form, a disjunction of groups, where every variable is just defined as a list of groups, where a group is a set of structural assertions. This requires a long sequence of normalization steps. And then we have the second step. In this second step, we transform each group into a generator, a machine to generate witnesses. This is quite an interesting step that we are going to present in the next slide. And finally, we run a bottom-up fixed point computation. We associate each variable to a set of witnesses, to an empty set of witnesses, and then we use the witness generators in order to grow these sets of witnesses up to a fixed point. And now we conclude with some words about how we transform a group of assertions into a witness generator. So we start from a set of assertions which have a complex interaction, the one with the others. For example, here, this assertion tells me that if I have a member whose name is AA, then this member must have a type X and may be used to satisfy this requirement, provided that it also has a type satisfying Y. We solve this situation of mutual interaction by providing a list of member description, abstract description of all members that may be used in the produced witness in order to satisfy the requirement. And we build a bipartite graph that relates the member descriptions to the requirement that they will satisfy. So, for example, this description AA will satisfy the first requirement, but not the second one, while this member description A, whose type is both Z and Y, would satisfy both requirements. And at this point, we are done. In order to generate all possible witnesses, we must just enumerate all possible solutions to a hitting set over this bipartite graph. And that's the basic idea behind our algorithm. Thank you.
Having talked about the theory behind, let's see the tool in action. We start with witness generation for a single schema. This schema is also discussed in our demo paper. Upon the push of a button, we can generate the first witness, and yet another, and yet another. Note that this schema uses the NOT operator. Many related tools for manipulating JSON schema struggle with NOT. Internally, our tool translates the schema into an algebraic expression. From the algebra, we can always translate back to JSON schema. When generating a witness, we first apply NOT elimination. This pushes the NOT operator down towards the leaves of the algebraic expression. Based on the negation-free expression, we can then generate witnesses as described earlier. Regarding open research questions, one concerns algorithm design. Currently, our tool is backed by a plain vanilla implementation, and there is lots of room for optimization regarding runtime and memory consumption. Another concern is algorithmic complexity, so specifying tight lower and upper bounds. In our online tool, we provide a set of example schemas for you to play with. You can generate witnesses, translate to the algebra and back, eliminate negation, and check two schemas for containment. And with that, we conclude our demo. See you at the Q&A session.